Okay, in this video I'm going to talk about the life cycle of a star. Life cycle of a star. Okay, which is found in unit P1. Right, anything I mention on this piece of paper is going to be foundation tier, and when I get the other piece of paper out, that's going to be the higher tier stuff. Okay, what you need to know is all stars begin their life as a huge cloud in space of hydrogen gas, and that cloud is called a nebula. Okay, so what happens is this is mostly hydrogen gas, and gravity, so the hydrogen will all start pulling on itself. Gravity starts to make it condense, and what happens is it will condense to a point where the temperature will rise, the hydrogen nuclei will be flying around really quickly, and what will happen is the hydrogen nuclei will come together and they will fuse together. And when that happens, that's called nuclear fusion. When that happens, we end up with something which we would recognise as being like a star in the sky, like the sun. We say it's in its main sequence. Okay. Now, in the main sequence, hydrogen is being fused together in a complicated process, but eventually makes helium. Now, what you'll notice is, or you should realise, that hydrogen, the nucleus of a hydrogen atom, is basically a proton, which is positive. So if you try to get two protons to come close to each other, close enough that they will actually combine and fuse together, that's not going to happen easily at low temperatures. It's not going to happen at all at low temperatures because these protons won't be moving fast enough. So fusion, nuclear fusion, there we go. Nuclear fusion only happens when these protons are moving fast enough that they can get close enough to fuse, okay, to overcome that electrostatic repulsion. So what happens is when they do fuse, if you get two protons to fuse together, they release energy, okay, and that energy will be in the form of electromagnetic radiation, and that's what gives us the heat and light from the sun. So the sun is not on fire, the sun is not burning anything, it's just nuclear fusion taking place which releases this energy. Okay, that's supposed to be energy. Right, so this is still foundation tier, you need to know this for foundation, but I'm just going to show you this because I'm running out of space. If we think about the main sequence, so if we imagine that's the sun in the main sequence, well, you might think, well, why doesn't the sun, because of gravity, why doesn't the sun just collapse? Because obviously gravity is pulling it in on itself. So why doesn't it all just crunch in and collapse? Well, the reason is because the nuclear fusion process, which I've just spoken about, that happens, that produces something called radiation pressure. And radiation pressure pushes outwards. Okay? And when gravity is the same size as the radiation pressure, the forces are balanced, and so the star in the main sequence will stay the same size. But obviously we've only got so much hydrogen to begin with in this cloud, and it's not going to last forever. Well, the main sequence is the sun right now is in the main sequence, and it's 5 billion years old, the sun. And it's got about 5 billion years worth of hydrogen left. So there's plenty of time for the sun to be in existence for another 5 billion years, plenty of hydrogen. But when the hydrogen starts to run out, then nuclear fusion will stop. And when nuclear fusion stops, we haven't got that radiation pressure. So this outward force won't exist. Okay? So all we'll have left is gravity. So what will happen then is, when the star in the main sequence runs out of hydrogen, it will collapse. It will just completely crunch in on itself, and it will have a very hot core. Okay? And the core will be hot enough at that point that these helium nuclei, well, they will start to fuse them. Now, getting a little bit higher tier, but helium nuclei are 2 protons and 2 neutrons. So to get 2 helium nuclei to fuse, they're going to have to be moving even faster than hydrogen nuclei, because these have got twice the amount of electrical charge that these have got. So to get 2 of these to come close enough together, it's going to be harder. So it's going to have to be hotter. So without nuclear fusion, the main sequence star will collapse. When it does, the core gets really hot and it blasts out these outer layers, so we end up with something called a red giant. Okay? And the red giant, the surface is quite cool, cooler than the sun's surface, or cooler than the main sequence surface of the main sequence star. But the core is really hot, as I've just said. So what happens is helium will fuse together at this stage to make elements like carbon, as heavy as carbon. And then once the helium runs out and we've got this carbon, the red giant will collapse and it will make something called a white dwarf. Okay? And the white dwarf is basically a hot star which will just shine until it cools down, and then it will become something we call a black dwarf, okay, which is basically like a lump of carbon in space. Now, a few times there I've said the sun when I've pointed at this one. That's because this is the route through. This is the life cycle of a star for something the same size as the sun. So the sun is currently at this stage and it's got 5 billion years left at this stage, but any star roughly the same size as the sun would follow this path. This is what it's destined to do. Now, when I said if I move on to another piece of paper, it's because I'm going into higher tier. It's because the higher tier people would need to know the life cycle of a star, which is much bigger than the sun. Life cycle of a star which has a mass greater than the sun. Well, obviously, it's sort of the same to an extent at the start. You start off with a nebula, but this will be a bigger nebula. It'll contain more hydrogen because this is a bigger star. It will go into something which in the main sequence is a bigger star than the one before. So this, again, hydrogen fusing together to make helium in that nuclear fusion process, releasing energy. We've got radiation pressure and gravity like we had before. Once the hydrogen runs out and we've got helium, then same thing happens as before. It will collapse, the outer layers will be blasted off, we'll end up with something called a red supergiant. Okay, and in the red supergiant, helium fuses to make carbon, maybe oxygen. Okay. Now, for something that's about maybe 3 times the mass of the sun, so let's obviously this is true for anything that's greater than the sun, like a mass greater than the sun, maybe twice the size of the sun, and it will follow this route. But if it's 3 times the size of the sun, it will go to a neutron star. So after this stage we'll end up with a neutron star, and a neutron star is where the protons and electrons will merge. Okay, so we'll end up with something which is just purely neutrons. And how this happens is because after the red supergiant stage, this will run out of helium, fusion will stop, you'll have no more radiation pressure, and this will collapse. And what happens is it will do this thing we call a supernova, which is basically an explosion. So if we imagine that star explodes, then when it sort of collapses in on itself, the temperature will go that hot and everything will be moving that fast that things will be moving fast enough to be able to overcome any positive repulsion. So the nucleuses or nuclei of all these different elements will all start to combine, and it's in this stage where heavy elements are made. So basically stars are like sort of element factories. They start off with hydrogen in space as a cloud of gas. Gravity takes over, fusion starts, the star goes through its life cycle, basically at each stage making heavier elements, and the heavier the star, the heavier the elements that are sort of produced at the end of it. So when a star gets to this sort of stage and it's a red supergiant and then it collapses in on itself after it's run out of helium, it can collapse to become a neutron star, okay, or if it's maybe 3 times the mass of the sun, or if it's about 10 times the mass of the sun, or should I say between 3 and 10 times the mass of the sun, or heavier actually, greater than 3 times the mass of the sun, it will become a black hole, okay? And a black hole is where it all just collapses in on itself. It has, you can't measure the density of black hole material. It's just almost infinitely dense, and it all collapses in on itself, and that's its fate, black hole. Okay, now black holes, they're so massive, they have so much mass and they're so dense that they distort the space around them. They're so heavy that light can't escape from them. Basically, that's the root through for a heavy star. Okay, so we've got star like the sun, nebula, main sequence, red giant, white dwarf, black dwarf. A star heavier than the sun would go, if it was about 3 times heavier, nebula, main sequence, red supergiant, neutron star. But again, if it was more than 3 times the mass of the sun, it would go nebula, main sequence, red supergiant, black hole. Okay. Now, the things that I've seen asked in past paper questions are, it could be something basic recall, it could be to explain what a nebula is, it could be to explain nuclear fusion, it could be to explain why nuclear fusion only happens at certain temperatures, and that's because the nuclei are going fast enough that the actual protons can overcome repulsion to fuse. Or it could be this business about radiation pressure. So why does the sun stay the same size? Why doesn't it just collapse in on itself? Because they represent gravity, them arrows, because you've got the radiation pressure pushing outwards, which balances gravity. Okay? So, hopefully that's useful.